Here is Phil Boyland from the University of Florida, who would be telling us about something where there's no title.
Thank you, Cap. So I'm going to start, I'm starting by showing this movie, and picture is 1,000 words, the movie is 1,000 pictures. So there's these two stirring protocols. This is actually quasi-stationary Stokes bit. Yes, sir. Microphone, turn it on. Thank you. So this is done by Matt Finn. It's actually quasi-stationary Stokes flow. But there's two stirring protocols that we're observing. And the only difference between them, so both of them turn the right two stirrers around each other in a clockwise direction. But the difference is the left one turns the left two counterclockwise, whereas in these they're turned clockwise. All right, so for Stokes flow, they're energetically the same, but you can see the consequences of the motion of the stirrers is quite different. And the thing that I'm going to be pointing to many times today is the way the material lines, which are passively transported here, they're advected passively in the fluid, how their lengths are growing. So the applications and the theory are all based on the growth of the lengths of these. And this growth, as you can probably observe, is linear, whereas this growth is exponential. And in fact, you can prove rigorously the rate of exponential growth and compute it and apply it, which I'll tell you about today. So here's an experiment that was done by Mark Stremler here. And this is, again, glycerin with dye tracers. And we do the same protocol, and not surprisingly, the same thing happens. And there's 9 iterates, and you can prove, for example, that if they still had their integrity, the dye tracers would increase in length by 5,600 in the left picture. So you can see there's obvious implications for mixing, but that's not what I'm going to be talking about. But in fact, Jean-Luc and Mark were talking later in the conference, and part of what they'll tell you is about the implications for mixing. So get my technology in order here. So, there is the title for the chair's satisfaction. So there's 2 parts of the talk. It's rather split into 2 pieces. One is strictly what in fact could be called topological kinematics. So I'm going to tell you some theorems and facts from dynamical systems and topology, and then I'm going to apply them to Euler flows. So there's really 2 distinct parts. The first, as I said, is strictly kinematic, but it's topology and dynamics. And there are some main ideas which I've already emphasized to you. One is that the...
Control L.
Thank you. The one is that there's this growth that's going on, but I'm going to be talking about 2-dimensional, 2 types of growth. One is topological in character, which is highly computable because topological data is usually quite coarse, and that means it's quite computable in practice. And it's not so applicable because it's kind of a little loose, but in fact, it gives a lower bound for the metric growth. The metric growth means the actual growth in the lengths of the material lines, and that's the thing you can put to use in fluid applications. And the topological growth will be a lower bound for the metric growth. So that's the main ideas to keep in mind here. So here's the first part where I'm going to just set up definitions and notations. And again, this is all at first strictly kinematic. So for me, a fluid region is a smooth 1-parameter family of multi-connected compact planar domains. There's a picture. You also saw a picture previously. So it's the complement of the stirrers is called M sub t. So again, the protocols we're thinking of, the outer boundary is fixed and the inner boundaries move. And the stirring is periodic, so that means the regions come back to themselves after time 1. And I'm going to call them a stirring protocol, as I already did. And the inner boundaries are called the stirrers, and they don't have to come back to themselves. Perhaps they're permuted on each cycle. So what I'm going to call a fluid motion, so you have to excuse me because my my training is in dynamical systems, and when we say flow, we mean what you mean as a steady flow, an action of the reals. So I'm going to call this a fluid motion, and at first, again, it's just kinematics. So it's just a family of diffeomorphisms. So you should think of this as a Lagrangian advance map. So you start at a point at time 0, and at time t, you're at the point phi sub t. So formally speaking, this is a differentiable injective map from the initial fluid region to the final fluid region. And the velocity field, of course, you get by taking a time derivative of the motion. And we have boundary conditions, so it's very important for the application. The fluid doesn't penetrate the boundary. So we have non-penetration of the boundary. And again, to emphasize this, the velocity field is just a velocity field. It doesn't have to satisfy a differential equation. And in certain special cases, we can use what's called a Poincare map. So it's important for what I'm going to say later that, as you all I'm sure know, if you stir a fluid periodically, you don't of necessity give rise to a periodic velocity field. Sometimes you do, sometimes you don't, and that's part of what I'll talk about. But if you do, then you can take the time 1 map and just iterate it in the way we do in dynamical systems to understand the dynamics. All right, so this is an important distinction about when the time dependence of the velocity field is periodic. So I'm going to describe a material line in the fluid just by an arc or a simple closed curve. So it's just an arc in the fluid. And I'm going to compute its length, as I told you already. So formally, we need a Riemannian metric to do this. They change with the region. And then the metric growth rate is just the rate at which this particular material line is growing in length. So it simply means we take the material curve, we passively advect it for a while under this fluid motion, and then compute its length. All right? So in dynamics, the growth of this quantity is very important. It's connected to the entropy and the Lyapunov exponents, etc. But I won't be kind of going into that too much. And this term in the denominator, this L sub naught, is just to normalize the growth. All right, so this is the metric growth, which is the actual physical growth of the curve or the material line. Now, as I mentioned at the beginning, there's also something called the topological growth, which is much coarser, but on the other hand, much more computable. All right, so for that, so let me first talk about this physically from this picture. So let's say we've advected the fluid for a while, and our curve gamma looks like this. And I say, well, that has a long metric length, but topologically, in the complement of this, in fact, I can shrink it by sliding this there, sliding this around there, and getting this. All right, so in topology, this is called a homotopy, and it's good to think of it physically just as a rubber band, but it's allowed to slip along the boundary. All right, so when I compute the topological length, which I'll define in a second, is I shrink the thing back to its minimum length. And for people who know Riemannian geometry, I'm just passing to the geodesic in the homotopy class. Whoops. All right. So a second thing I need to do to make this topological is I don't want arcs whose ends are just floating around in the fluid because they're not tied down. So there's a certain class of material lines I'm going to consider, and these are the ones you saw we used in the experiment, but they connect the stirs to the boundary, or else perhaps they're simple closed curves that go around a boundary. So I don't want to consider things which just go around one hole, because that hole's going to move around, and topologically you're not going to see anything from it. All right, so these are the essential material lines, the essential simple closed curves, or arcs. And so here I'm formally defining what I have in the picture here about the type of deformations I allow you to do to shorten the curve. And having done that, then we compute the least length in the homotopy class. So again, all I'm doing is I'm declaring that I can try all possible things I can get by deforming this, keeping its edges on the boundary, and this is the shortest, so I declare that to be the topological length of the curve. All right, or the arc in this case. So again, to compute the topological length, at each stage, at each time, I evolve for some time t, shorten it, and measure that length, sometime t, shorten it. So I'm not seeing all these secondary foldings. All I'm seeing is the essential topological winding of this thing in the space and in the fluid region, and that's what I'm measuring. And it's the growth rate of that which I'm going to compute, all right? So this important remark that I made at the beginning is that the topological growth could actually be 0, for example, or it could be something, but the metric growth is always bigger than that, right? Because here we've taken infinitum. We shortened the thing as much as we can, all right? So this growth is actually bigger, and this is the one we're going to put to use in our applications. All right, so this is, so these are just some comments on it. The first is, again, if you think about this a little bit, is as we move these things around, because we're always shrinking, we're passing to homotopy, that in fact, it doesn't, if I switch these two around, it doesn't matter if I switch them like this or like this. As long as I switch them like that, I'm going to get the same growth rate. So in fact, the dependence of the topological growth rate on the stirring protocol is really only on the topology of the motion of the stirrers, all right? And how that's formalized, as I'll tell you in a little while. But a second bit of topology here to throw in is that it doesn't depend also on the details of the fluid model. So if I move my stirrers in a certain way, and then I throw in a body force, all right? And then after some time, I get a different advance map, it's still topologically the same. And in fact, we're going to still get the same topological growth rate. All right, so you have to kind of really change the topology of the motion of the stirrers in order to change this topological length and topological growth. So there's a theorem that we couldn't do anything with this unless I keep telling you that we can compute and estimate this topological growth. And you saw, in fact, in those two pictures I showed you, this was a topological growth that was exponential, and this, it was linear. So that's what the Thurston-Nielsen theorem. So Thurston proved a quite more general theorem in the 70s, and Nielsen back in the 30s began the theory, is basically classified, in this language I say isotopy classes, but in the language of this it's stirring protocols. He classified the stirring protocols into categories, whether they force exponential growth of the topology or just linear growth of material lines. And this is all topological. It's not metric. All right, so let me state the theorem for you and then remind you in the pictures. So here's a formal statement of the theorem. So let's say we have a stirring protocol. We have a stirring protocol, so that means it's some motion of the stirrers. And again, strictly kinematic. We just have a fluid, and the important thing is it doesn't break. It doesn't split, and it doesn't pass through the moving boundaries. So there are three cases. The first is that you have exponential growth topologically. That means that if we take any material line, it has to be essential. It has to be connecting the outside boundary to an inner boundary, and we let it evolve in time. It grows exponentially with a rate bigger than 1, which is called the dilation. All right, so this is the first case, and it's connected to Anosov diffeomorphisms, if you know about them. But here, just think of it as a name. So pseudo-Anosovs are associated with exponential. So certain stirring protocols always imply exponential growth, all right? And that's the basis of most of the applications. The second class is called finite order, and these guys only imply linear growth, all right? So that was the second protocol here. Whoops, how'd that happen? Oh, sorry. I got ahead of myself there, but this is good to show here before. So on the left, you see exponential growth in lengths, and here you have the right, and this is the exponential, this is finite order, this is pseudo-Anosov. All right, and then the third case, which I'm not going to talk about, I won't define, is basically you can imagine you could make a protocol that does on the big scales, it does one of these, but then there's 3 stirrers inside, and then the small scale, it does that. So So you can combine these protocols into pieces, and that's called reducible, but I'm going to focus on these two cases. All right, so let's go back here. So once again, I keep showing these pictures because they make the point better than I can, is that we have two protocols very similar, but one is causing exponential growth, and the other is causing just linear growth. It's just spinning, and this one is kind of wrapping, okay? So there's the apparatus, which I showed at the beginning, I hope. So here's some things to say before I put this to use. The first point is that this is, again, this is topology theorem, all right? And the first point is that every essential growth curve has the same growth rate. So it's very powerful in the sense, I mean, it's topology in the sense that it's just the topological length, not the real metric length. But every essential curve grows at this rate, okay? And as again, I keep saying, because this is the main point, the topological growth is a lower bound, and the metric growth could in fact be much larger. So maybe Jean-Luc will talk about this. This whole theory gives a lower bound for the growth, but in fact you can have other things operating on top of it which cause secondary folding, and then you can have larger growth rates. And again, for the sake of applications, the point here is that the lower bound is exponential, right? So we have an exponential lower bound on metric growth rate, and that's what we're going to run with in the applications. And the other bit is that this is all completely computable. So there's a machinery developed over the last 30 years to get analytic expressions or very, very fast numerical answers, which Jean-Luc knows how to do and has pioneered, from the motion of the stirrers. So the stirrers, again, I didn't tell you about a braid because I'm kind of pressed for time here, but the idea here is you can draw a picture of the braid by of the stirring protocol by looking at its time trace. So these split like this, goes up like this, these like that. So there's a whole kind of combinatorial way to describe the stirring protocols, and from that you can compute all these magic things, this dilation and other stuff where people know dynamics, invariant measures, periodic orbits, lower bounds on the entropies, and all such things. All right, so this, again, points are it's all computable, and we have an exponential lower bound. All right, so here, I was getting a little ahead of myself here, is that this all depends, as I've said several times, just on the stirring protocol, and in fact, technically on the isotopy class of the motion. And here are the braids of the two stirring protocols. I might have, no, they're the correct. So here, these split like this, and then these rotate like this, whereas over here, you rotate clockwise, then clockwise. All right, so this very nicely encapsulates the stirring protocol, and in fact, the collection of braids is a group that has been much studied, and it's from the combinatorics of the braid words, the description that you can compute these exponential growth rates, or the linear, or the fact that you only have linear growth. So here's a nice picture that I stole from Jean-Luc and Matt, where here you see a curve here, an essential curve, and it's passively advected up, but the motion of the stirrers, this is of course time going up, gives rise to this very complicated wrapping pattern, which is similar to what we saw in the previous mixing. All right, so that all, as I said, is all kinematics. It's all topology. But because it is topology, because our fluid is an unbroken continuum, and it doesn't pass through the boundary components, we can apply it to basically any fluid model, Euler flow, Navier-Stokes, Stokes, body forces. It works for all of them, all right? But for Euler, there's a very special fact that allows us to apply it, which you all know. This is wonderful Helmholtz theorem, which I'll remind you in a second. All right, so now we're no longer doing kinematics. I'm going to just focus for the rest of the talk on Euler fluid motions. And I apologize for saying fluid motion, not flow. So now we're going to satisfy the Euler equation, divergence-free, constant density. I have the moving boundary. So these are the Euler flows, Euler fluid motions. And as we all know classically, that we can describe the velocity field by its curl, which in this case is a scalar, which is important. And because we have a multi-connected domain, we have to be careful to specify the circulations around the boundary. And then, given this just says what everyone knows, that we get a unique divergence-free field with the appropriate boundary conditions from the curl. All right, so as is so important in two-dimensional Euler and fluid, is the curl is the main thing, the vorticity we're going to work with. And just a theorem here, there's classical solutions when you have these moving boundaries. And my attitude is just going to be that you have classical solutions for all time with the same regularity as the initial vorticity. All right, so I'm not going to deal with the issues of regularity. So all these theorems, all the theorems I'm going to tell you, I'm going to treat the vorticity as a parameter. So in dynamical systems, one of the main themes of modern dynamics is that the collection of all dynamical systems is too complicated. So we look at what's called a generic set. So you look at a thing that's typical. So dense G delta in the topology, if you know what that is. So I'm going to think of the set of Euler flows as parameterized by their initial vorticity, and then show you what you can prove if you assume generic or typical initial vorticity, because you'll see how this comes in. All right, so that's the philosophy of the theorems that are coming up, but I was getting ahead of my little self a little there. And as I mentioned before, for our applications and for, of course, much of two-dimensional fluid, the important tool is to work with the vorticity, and it's transported passively exactly when it's in Euler fluid motion, and we have to watch out for circulations around the boundary. Okay, so I'm going to first give you a theorem this is a theorem now about linear growth, all right? So this is all these theorems are about growth rate of material curves, and they're all based on assumptions on the nature of the initial vorticity. All right, so I'm going to just show you this first theorem, and this actually, in fact, doesn't use the Thurston theorem. This, in fact, just uses the transport of vorticity, but it's a linear growth theorem, and it kind of fits into the pattern that I have of linear growth and exponential growth, and I'll tell you at the end how they all fit together. All right, so again, using language that I'm familiar with, the Helmholtz-Kelvin theorem says that the vorticity is passively pushed forward. All right, so this is in our language, we push it forward like that. Now let's make the additional assumption that the velocity field is time periodic. All right, so again, this may or may not happen, but let's assume it does happen. In which case, then the vorticity at time 0 is the vorticity at time 1, and this is the same. And so the vorticity to start with is the same as the vorticity after omega naught is a real valued function. It's what's called an integral of motion. It's a constant of motion. It's preserved along orbits. Now, 2 dimensions is rather small, right? If you have a preserved quantity for a map, it very much restricts the dynamics. All right, so Brown and Samuelson observed that there's a theorem of Moser saying that if you have a real analytic integral of motion, then you can't have what's a homoclinic intersection. So I'm going to kind of jazz that up a little bit and tell you about growth rate. All right, so again, we're thinking of a time periodic stirring protocol, and it gives rise to a time periodic Euler fluid motion. So again, I'm going to tell you in a little while, sometimes, as many of you know, that absolutely will not happen, but let's assume it does. And let's look at the initial vorticity and assume it's generic. So let's say it has finitely many critical points. Then the theorem is that there's a constant so that all the growth of all material lines is linear. So it's bounded above with a linear bound. All right, so this metric one-dimensional growth is linear, and then people who know dynamical systems know that this implies kind of trivial dynamics, no entropy, most of your Lyapunov exponents are 0. All right, so this is the linear growth theorem. And let me say it's important that we understand what it doesn't say. Well, the first comment is clearly This is a very general result. It's simply two-dimensional time-periodic Euler flows. But notice I'm not telling you that generic initial vorticity gives rise to a time-periodic Euler flow. And it doesn't even say that amongst the initial vorticities which do give rise to time-periodic Euler flows, sorry, I'm missing something there, linear growth is typical, right? So I've asked people this, and it seems to not be terribly well understood just now, is how many time-periodic Euler fluid motions really are there that aren't steady? I mean, is this a theorem about the empty set or a very small set? All right, so those of you, most of you, I'm sure know in 3 dimensions, if you have a steady Euler flow, that in fact you preserve the Bernoulli function. And so in that typical case, when you're not a Beltrami flow, then you also have 0 entropy. So this was very much inspired by this 3-dimensional result, classic result of Arnold. All right, so here's the idea of the proof. I'm afraid the picture's a little vague there, but I already said it, right? So if the vorticity is typical, it has level sets that are one-dimensional, right? There's a finite number of critical points of the vorticity, but you have nice level sets. They're preserved by the dynamics, and dynamics in one dimension are very simple, right? You can't, injective dynamics, invertible maps in one dimension. So that's the idea. So this is a more technical thing. Let me kind of skip that. All right, so let me tell you where we are so far. I kind of have 2 tools that I've introduced here. One was the Thurston theorem, which tells you that in certain stirring protocols, you always have exponential growth. All right, so you always get exponential topological growth, and therefore you always get exponential metric growth for certain curves. On the other hand, I've told you that time-periodic velocity fields with typical initial vorticity give just linear growth, linear metric growth. All right, so these can't live together unless it's the case, as I said at the very beginning, and it's what's sitting here, is that if you stir an Euler fluid with a periodic but pseudo-Anosov, so think of stirring an Euler fluid with this pseudo-Anosov stirring protocol, I'll show you a picture again in a minute, then it can't give a time-periodic solution to the Euler's equation, right? Because if it did, with typical initial vorticity, you couldn't have growth, all right? So in fact, you can kind of use the exponential growth to get an estimate, and in fact, to show that, in fact, the gradient of the vorticity, or the C2 norm of the velocity field, is going to infinity exponentially. So it's very kind of not periodic. So let me state the theorem in this case. So again, we start with a stirring protocol, the type I'm talking about. It's a pseudo-Anosov. We have some initial vorticity, again, generic C2 function. It wouldn't work if it was constant, if it was irrotational, which I'll tell you about in a minute. So this isn't valid, of course, for irrotational fluids. Then there are constants so that the gradient of the vorticity grows exponentially, and also its L1 norm grows exponentially. And this lambda is the dilation, which we can compute exactly. All right, so you get growth, and this is infinite time growth. Again, I'll emphasize, this is over infinite time. You get rigorously that these guys have exponential growth of the gradient of the vorticity. This is a supremum here. And of course, then you can just fool around and you get all these other norms going to infinity. So here's the idea of the proof. I've more or less already explained it. So the first thing to do is to find the initial vorticity, which gives a nice band of the level sets of the vorticity. All right, so then you have to fool around and show that a typical function, the typical real-valued function on a multi-connected domain has little bands or else little annuli where you have layers of level sets of vorticity nicely layered up. All right, so the second thing is then we hit it with the protocol, and we know because this is essential, right? So this is connecting, I should have put a boundary component here. This is connecting a boundary component to a boundary component. Since it's essential, then it grows exponentially topologically. Therefore, it grows exponentially metrically. All right, on the other hand, this is an incompressible fluid. So in fact, this little band's area is preserved. So if you preserve the area and make it very long, what has to happen is the level sets of the vorticity have to get closer and closer together, and everything is exponential. All right, so again, this is the idea of the proof. The thing stretches, then the level sets of the vorticity have to be squished because it preserves the area, and then that implies when the level sets of a function get very close to each other exponentially, that's exactly saying that their gradient is growing exponentially. So that's the idea. And, oops, I didn't put in the other picture. So let me go back here to these experiment just to make it clear. So again, so if you want to think about this theorem, instead of thinking about these as die tracers, just think of them as level sets of the vorticity, right? So the vorticity is transported in an Euler flow just like, you know, a die tracer in a Stokes flow. And then there's the picture, right? So after 9 iterates, there's the layering, the level sets of the vorticity, and between them are the other values of the vorticity. So it makes it very clear what's happening, why the gradient of the vorticity is growing exponentially. All right, so let me go back to where I am and make some comments. How many of you know there's a lot of such results in the literature, and Udovich and others have shown the linear growth of this gradient for perturbations of many steady two-dimensional Euler fluids. And these, of course, is a very important part of stability analysis. Arnold and Friedlander and Wiesik and others have also worked with the exponential growth of the distortion and also for stability. And that's really what's going on here. So if you kind of see what this is doing on the analytic level, is that, again, excuse my notation, this is how I would write it. This is the derivative of the Lagrangian advance map, and this is how the gradient of the vorticity is transported. We're stretching things exponentially, so that means the spectrum of this guy is growing exponentially. In another direction, it's shrinking exponentially. So you're hitting something with exponentially growing eigenvalues by a generic vector. It's going to grow exponentially. All right, so it's the same mechanism, which everyone, well, I'm sure everyone understands, is you have exponential growth of the distortion, or the, what's the proper word here, the distortion, then you're going to get exponential growth of gradients of any transported scalar, in particular the vorticity. So here, I just wanted to say something a little more speculative about this. So there's something, at least in part of the literature, is called the Udovich conjecture or hypothesis, which is that if you look at generic, again, this is a kind of typical statement, and I've turned it into a version that I like, is that for typical initial vorticity, you have this exponential growth of the gradient of the vorticity. All right, so how could we understand that? Again, this is just providing you with I wanted to give you something topological that, you know, from this that would work in general. So here's the idea. So there's basically two ideas. One is that if you take, you know, any Euler flow, there's going to be points that wrap around each other. Unless it's very special, there's going to be some collection of points that braid each other in a complicated fashion. Again, reasonable, but probably impossible to prove. All right. The second thing is that even if these points aren't kind of periodic stirring protocols, they're still going to cause exponential growth, right, of material lines. And since, again, vorticity is transported, it's going to cause exponential growth of the gradients of the vorticity. All right, so it's from a topological point of view, all that's kind of embedded in this idea of generic exponential growth of the gradient of the vorticity is that there are material points that are braiding around each other in a complicated fashion, which, again, one expects typically to happen. And again, as a mathematician, I have to say that's probably baloney, but it's a good idea, I think. All right, so the last bit here is talking about a dichotomy here. And again, some part of this was certainly inspired, as I said already, by what Arnold did with steady Euler flows in 3 dimensions. So let me remind you again, a version that I'll tell you here is that for typical vorticity, the preservation of the Bernoulli function implies that the flow is integrable and typical orbits are combined to invariant tori and annuli. All right, so this is kind of the typical case, the non-Beltrami case. All right, whereas there is an atypical case that's quite interesting, and those are the Beltrami fields where the curl is parallel to the velocity field. And in this case, you can have chaotic dynamics, positive exponents, and knots, and other things, which we'll be hearing about this week. So there's a somewhat similar, I'm going to present at least one version of a dichotomy like this for two-dimensional Euler fluids. And this is what we've seen today, is the first bit we've seen already, which is that for typical initial vorticity, again, this is all time periodic. So I'm back in the world of assuming they're time periodic. Just as here, of course, we assumed it was a steady three-dimensional flow. Now, the two-dimensional analog that, in many ways, is a time periodic two-dimensional Euler flow. In the typical case, as we've seen already, we have the linear growth theorem. So what is the atypical case? So one atypical case is, as I've already mentioned, is to have constant vorticity, right? So if you take, this is the next slide, but you take a periodic stirring protocol, and at each time you just solve the Laplace equation with the right boundary conditions to get a harmonic stream function that has zero vorticity, right? And then that's periodic, right? So if you have zero vorticity, then in fact you do have a time periodic solution. But if the protocol is pseudo-Nassau, it implies chaotic dynamics and exponential growth. All right, so this is a case where you can have a time periodic Euler fluid motion, but still have chaotic dynamics. And this is the case only when you have atypical vorticity, and the case where you can actually prove it is when you have constant vorticity. And then, as you know from, this is just the statement of the theorem, that you can, if you specify circulations as well as the constant vorticity, at each time you can solve the equation, get a periodic Euler motion with that constant vorticity, and because of the Thurston theorem, you get exponential growth of lengths of curves. And again, this takes another part of the theory, which I haven't told you about, but it also, the fluid has measures with positive exponents and lots of entropy and many other dynamical things you can say. So I think I will stop there. Thank you.
Questions? Steve?
I just wondered, the pseudo-Anosov stirring of the Euler flow, how is that done?
It is done as far as, well, first as a mathematician, it's done between my ears. Second, too, it was done numerically by Matt. And
For potential flow.
for potential flows.
Oh, no.
Right, so I don't know, I think someone actually did do that, where they did a pseudo-Nassau for an Euler flow. But I don't,
But when you said, in your theorem, you had pseudo-Anosov stirring, so you say that is being performed somehow.
right, so there's, right, it's not, right, so externally, you're moving the boundaries in a prescribed thing.
So you do have the boundaries there in the flow.
You do have the boundaries there in the flow, and then, right, when you're solving, right, then you just solve the Euler equation.
So it's an Euler problem.
Yeah, right.
For the three, I mean, without stirrers at all, if you have three vortices in an infinite fluid, then you have a periodic, quasi like the motion stirrers. The vortices move in a periodic manner. Now, presumably for some strengths, choices of strengths and initial orientation, you can get pretty well any braid you like from the three. And generically, that will be pseudo-Anosov, won't it?
I'll have to ask Mark. I don't know with three. We actually did study this with doubly periodic boundary conditions, and there was a whole parameter space. Some were pseudo-Nassau, some were not, and in fact, most were pseudo-Nassau.
With the doubly periodic boundary conditions, but I think the reason we looked at doubly periodic boundary conditions, if I recall correctly, is because with just three vortices on the plane, those all ended up being finite order. If you just look at the vortices themselves and just allow them to move under their own dynamics, I think those were all finite order because
four or more.
they amount to just sort of tumbling
Really?
past each other.
Oh. You have
Right,
to
when
go
we have
four
four or
You have to go
more,
to 4 vortices.
four or more, it's a different game, and doubly periodic, I think even with three. You had,
Right.
in a moving frame, you had to move into the vortex frame. But there was very elaborate braids, like braids with like 18 crossings. It was quite elaborate.
Also a question. Arthur.
I wonder what happens if the initial data for the Euler equation doesn't satisfy the assumptions of the theorem. So for instance, we have piecewise constant initial data, or perhaps like vortex patches, or unbounded like point vortices.
Yeah, so if there's areas of constant vorticity, then the theorem won't say anything. So, I mean, the topology is the topology, right? So you always get exponential topological growth, right? But what that says about the vorticity, well, if it's constant vorticity, you can't draw any conclusions from it. So that's kind of the part that's missing. But, you know, of course, that part is transported. That part, if it connects the two boundaries, then the patches will, in fact, be growing exponentially in length, etc. So, I mean, that's kind of the most you can do.
For 2D Euler, vorticity gradient grows as an effect of strain field.
Yeah.
So the problem is whether vorticity gradient align with eigenvector of strain field.
Yes.
If it is aligned, it's exponential. That's
Yes.
what you're saying, I think.
Yeah, so right, it is aligned in certain, you can at least show that certain places in the fluid it has to be aligned. And that's because the lengths of the level sets of vorticity are growing exponentially. So that could only happen if they were being lined up with the biggest eigenvalues of the strain. Right, exactly right.
Yeah, so you mentioned then in the Yuda-Nosov case, there is a open set where you have this metric mixing, metric exponential growth, yes? And possibly
Yeah, so, right, so,
set where it is linear. But from the picture which are above you, it looks like a more complicated thing than just domain.
yeah, so this, right, sorry.
Is it a theorem that there is a open set?
Yeah, so what the theorem is here, so, right, so the topological theorem is that there is a set, perhaps of zero Lebesgue measure, on which you kind of have this picture,
Yeah.
all right? And then elsewhere you throw up your hands and you don't. No.
Wait, so it is not a domain.
It's not necessary, right, it's not, so if it's just strict kinematics, it's not, now it happens that for Stokes flow, it seems to be, very nice, tight, you get the minimal amount of stretching, and you get this nice foliation. That seems to be the case for Stokes flow. Occasionally, it doesn't work. Now, you simulated Euler flows, but potential flow with the same protocol, then you don't get this at all. You get all jiggy and jaggy, you get elliptic islands, and all sorts of other secondary stuff. So that's why, so you always get exponential growth in these material lines, but there could be spaces between them. You can have elliptic islands. So the topology doesn't control all that. That's all geometry and kind of real.
Okay, so metrically it can be a poor mixing.
Yeah, metrically it can be poor mixing, right? So again,
Very good.
well, you'll hear some talks on,
Yeah.
so,
Another question. Do you have a single example or some proof that there exists really for this periodic protocol? There is a periodic solution of Euler, which vorticity is different from constant.
I do not. I have.
So it is all conditional.
It is all conditional, as I
Okay.
said. It could be a theorem about the empty set, and I'd hope to ask the audience, does anyone have such an example? Because I,
But don't answer now because we're out of time.
we're out of time, like the
Thank you very much.
Tell me later, but yes, absolutely. No,